This is the Turbidostat version 1.2, and the differences here has been that we added alternate drain logic. So there's two drain VIs supported now, a mass balance drain, which will literally just match what we feed in to what we drain out. And the assumption is that another system will determine the fermenter volume and either add or get rid of fermenter volume as necessary. And then a fermenter feedback VI, which directly measures the fermenter weight as well as the feed and drain. And this one here will be able to compensate for extra volume being added or removed to the fermenter during operation. The idea, of course, is that for a long run, there'll be acid or base solutions added. There may be evaporation or other external events that cause the fermenter to either gain or lose volume. The feeds is the same. The physical pump and scale support is the same. And we've done something here with the simulation area. The simulation we have, this was existing. We have a pump scale simulation and an OD sensor simulation. And we've added to this a fermenter simulation that allows us to adjust what's going on in the fermenter. Now this simulation is fairly simplistic in that it assumes either a constant gain or a loss of a small amount per iteration. So let's go and set this up. And normally what we would do is we would set up a feed, we would set up a drain, and then we would set up our pumps and scales. However, with no hardware present, we'll need to use a simulated pump and scale as well as an OD sensor and a simulated fermenter. So going over a few things just very quickly, in LabVIEW you'll notice that these guys here are LabVIEW controls, and this is the initial setup of the VIs that we're going to start. And these are all different arrays, and you can index through the array this way by clicking the up and down arrow here in the upper left-hand corner. And you'll notice that some entries in the array are clear and others are grayed out. Grayed out ones actually do not exist, but the ones that are clear are actually instances that exist. So in this case, we have one feed set up, and we've selected pump 0 for the feed pump. We've selected the OD sensor 0, and we've selected scale 0. So the feed then is going to operate using pump 0, scale 0, and OD sensor 0. We've also set up a threshold of 20%, where if the OD exceeds 20%, our pump will come on at 8.9 RPM. When it is not in excess of 20%, it will pump at 0. Now our drains here, there's an important thing to understand that right now the system supports either mass balance drains or fermenter feedback drains. At this point it does not support both. In the future we may set it up so that it can support both, but right now it does not. So in this case, this is grayed out up here, so we have no mass balance drains configured. And here we have one, you can see just one, fermenter feedback drain configured. And we'll change these, we can change these after it's running, but let's change it now. Let's change this to 1005 as our high limit. And our low limit, let's just set at 980, and these are all in grams. And here we're saying we are going to be monitoring feed pump 1. We're going to be looking at feed fermenter scale 2, and our drain pump is going to be motor 1. Now, you wonder why the drain here is going to be looking at the fermenter scale as its primary feedback. The reason we're looking at feed pump 1 is that the way the drain VI determines what to initialize its speed at is basically by looking at how fast the feed pump is running and taking an initial guess based on that for what the drain pump should be running at. I put the ratio here at 1 so that the idea is that the drain pump and the feed pump should be pumping the same amount per revolution. Now, real pumps, well, we don't have any. If we did, we'd have one set up with its communication port, its scan rate. Same thing with scales. If we had one, we'd set it up, but we don't. And so now our simulation, we have two pumps set up, a feed and a drain pump. So you see there's two things set in here. Pump scale pair 0 is going to be the feed. Its initial value will be at 0, at 5,000. And notice that it's going to be pumping out 2 grams per revolution. We go to the drain pump. We're initializing it at 0. It's using motor 1 and scale 1. And it's only pumping out 1.8 grams per revolution. What we're doing here is saying, well, these pumps should be matched, but they're not going to be exactly matched. And of course, there's no more there. We're going to be simulating one OD sensor, and this OD sensor is going to be reading off of a table. And so essentially, there's a table location here where we've got a CSV table that's essentially a spreadsheet that has the time value and the OD sensor reading in it. The simulated fermenter, the initial weight is going to be 1,000 grams. It needs to know the feed scale, the drain scale, and its fermenter scale. So it looks at the feed scale and the drain scale as inputs, and then writes what the fermenter scale would be based on that. So based on all these things, let's fire it up. Now, and what I've done here with visibility is I've turned on the visibility of a bunch of these VIs: the feed, the drain, the OD, the sim pumps, and the sim pumps and scales, and the simulated fermenter. So let's fire it up. And pretty soon all these windows pop up. Now, obviously, a lot of these windows wouldn't be here if we were using real hardware, but since everything's simulated, we might as well look at what we're doing here. Let's put our drain over here, our feed over here. I have to find my simulated fermenter. There he is. Put him there. Now let's start turning all these on. Turn on, come on. Turn on feed. There you go. Turn on drain. Turn on fermenter simulation. Now let's make this gain a little bit instead of lose a little bit. And the reason to do this is to ensure, well, our only source of extra volume and weight is the feed. And so the only thing we can do if the fermenter gets too light is to just not pump. So let's put it positive so that we can regulate a little more positively. Well, then let's turn this on. Now this is starting to run. We're at table index 0. OD is 0 right now because the value here is 0. Every 30 seconds it's going to be changing to a new value. And what we will do here, let me just explain a few things. We're going to just watch it run. This loss per gain in grams per cycle, 0.005 grams per cycle, that's 1/3 of a gram per minute. That's a fairly low loss or gain, but we expect it to be small compared to our feed and drain speeds. So now we're up to 10, and remember the threshold is 20, so we have to exceed 20 for the pump to come on. One of the things we're seeing here is the fermenter weight is creeping up due to this loss gain. Basically, it's going up by 0.005 grams per second. We're seeing that show up in the feedback over here with our drain control, which basically is showing us we're using our fermenter scale as the primary feedback. Now moved on to table index 2, which is 15. And we just sit here and wait and let this run. So of course right now nothing's really happening except the fermenter is very slowly filling. And when this gets above 20, which will be the next iteration at, I think, 120 seconds, the pump will then come on and we'll start seeing things actually happen. Notice these scales haven't moved yet because neither the pump nor the drain pump or the feed pump have started yet. So here we go, 25. We now start pumping. We see a total feed start to accumulate. We are now running on the output here, and the logic there is that when this VI noticed that the feed pump started, it decided to start the drain at the same speed. And what will happen is if we go outside the thresholds that we've set for the fermenter weight, then this VI will actively try to adjust the drain speed to bring things back in line. We can see here that we're moving here. This scale is incrementing slowly. This scale is decrementing slowly because, of course, we're pumping out of the feed vessel. Again, the reminder here, we're feeding just slightly faster than we're draining. And so we expect this value to go up over time because there's a mismatch. And in this case, there's both a mismatch and an extra feed coming in from this fermenter mass balance. So we can see this value slowly moving upward, and when it exceeds 1005, what we'll see is we will see this speed increase. Now, one of the things I haven't noticed is the step. When it goes outside of bounds, it uses the step and the high limit. High limit obviously is how fast it allows the pump to go, and the step is the different step sizes. Now the feed here is stopped because now it's moved back down to 20 again. We're still within the thresholds here, so at this point this pump turns off because it follows the feed as an initial guess, and since we're within the high and low thresholds, there's no sense in changing anything. We notice this is slowly moving up again because of the constant gain that we're getting from down here. Now it'll take quite some time using just this slight fermenter imbalance to reach the threshold, and we'll probably reach the next on-off. So the value is 20. We're moving up. Soon the pump will come back on. The feed pump will come back on again based on the simulated OD input. There we go, 25, turns back on. We're running back here again. This here moving up, keep our eye on that. Once it passes 1005, we'll see the regulations start to kick in. There we go. Now here we're starting to move up. Notice this will only increment by a step after a delay of 2 seconds. This delay really is simply to allow scales to settle and things like this. 2 seconds is, in our experience, generally more than enough for a scale to stabilize. Now, one of the things we're noticing here is that now we've railed. We're up against the output limit 10, and this is still moving up slightly. That means our high limit is a little bit low. Now, we could just leave this and let it accumulate, because what will happen is we're outside the limit and we can't really pull it back in with outside the high threshold. We can't really pull it back in based on our high limit being slightly slow. But however, eventually the DO will turn, OD rather, will turn off, and we'll be able to get back in alignment. But let's just pop this up to 11, pushing the up arrow, and this allows our output to adjust upward. And what we'll see is this is now coming down. Now, of course, the algorithm here is very simple, and so it's as long as it's above the high threshold, it's going to speed things up. At this point, actually, we're rolling back toward 1005, and as soon as we cross the threshold of 1005, it's going to return to just matching the feed input. So soon we'll see this go back to 8.9, which is, of course, what we're running here. And so now what this is going to do essentially is it's going to servo back and forth. Well, servo is probably a poor way to say it. It's going to regulate. Basically, it's going to slow down. Pump's going to speed up until it comes back below 1005, at which point it slows back down again. And this does create sort of a long-term oscillation, but it's a small oscillation, and we're dealing with rather large volumes. And what the idea here is it's not really critical to try to keep this within an incredibly small range. So eventually what's going to happen is we'll run off the end of the table. Index 18 is the last index. And what we're doing here is now we're basically oscillating around the high threshold, keeping this thing regulated. And then what will eventually happen is once the OD sensor data ends, it'll go to 0. And then what we'll do is we'll show that we regulate as well based on the small input from the fermenter mass balance. So here we're starting to pump again, and well, it's going to be doing the same thing. Speeds up until we see this number start coming back down again. There we go, we're coming back down. There we reset, and we're coming back up. And this will continue as long as we're feeding. Now we've come off the end here. The value is 0. So now what this is going to show is we're going to be, when we came off to 0, this feed pump stopped. We re-estimated at 0, and now we're slowly climbing back up again because we are still above the high threshold. Now we're below the high threshold, and we go back to 0, which is the feed pump speed. And it's going to slowly creep up again. And here we go, we're starting to regulate again. And we'll watch this 1 or 2 times. There we basically are, obviously things are moving much more slowly now, because of course the only difference is being driven by this constant gain of, 0.3 grams per minute. And so what's happening here is every so often the pump has to turn on, the drain pump turns on quite slowly just to keep the thing close to 1005. So at this point, the system is in steady state. We're no longer driving the OD sensor. Well, what we've shown is that when the OD sensor is running, we can regulate. When it's off, we regulate as well. Judicious selection of the high limit here and some of the speeds involved obviously affect the amount of oscillation we're going to get in the volume or weight, which is what we're really regulating on. But as I said before, the point here is that the amount of feed that we give is critical based on our OD sensor. But the absolute volume or weight of the fermenter really just has to be between a reasonable bound. So at this point, this is how the system works in fermenter feedback mode. If we were doing mass balance mode, it would be like one of the earlier videos. However, we wouldn't have this simulated fermenter mass balance because in mass balance mode, what's happening is we're literally just matching our feed to our drain, and extraneous volume changes to the fermenter aren't going to be handled by our system. So let's stop this for now.